Okay, so now let's look at the case of linear two-point boundary value problems. Okay, so that looks like x double prime is equal to u of t plus v of t x, right, plus w of t x prime, and then x of a is equal to alpha, and x of b is equal to beta. Okay, so this is a boundary value problem. And let's assume that we have the solutions, that x1 and x2 are two solutions of the differential equation. Okay, so since it's a linear ordinary differential equation, when you have two solutions, then any linear combination, it's like of those two solutions are again a solution of the differential equation. Okay, so then y of t equals to lambda x1 plus 1 minus lambda x2 is also a solution. So here it's like we haven't taken an arbitrary combination of this. And the reason is because if you took an arbitrary combination, it would satisfy the first equation, right? Because it's a linear differential equation. But it wouldn't actually, even that's not true, right? It's like, because you have this u of t here. So if it was homogeneous, which is to say that u of t wasn't there, then any combination of x1 and x2 would be a solution. Okay, but because it's like there's this inhomogeneous term, you have to take convex combinations, right? So you have lambda and 1 minus lambda, so the sum of this is 1. Okay, so this is a convex combination of x1 and x2. And when you have a convex combination of solutions of a non-homogeneous linear differential equation, it doesn't have to be constant coefficient, then it would again be a solution of this non-homogeneous linear differential equation. Okay, in addition to that, because of the fact it's a convex combination, it's like it also satisfies the boundary conditions as before. Okay, so all right, so the bottom line again is that if x1, x2 are solutions of this boundary value problem with these boundary conditions, then this combination is also a solution. Actually, let me just put it as the boundary value problem. Okay, which is to say it also satisfies the boundary conditions. Okay, you can check this. Right, if you have u of t plus lambda v of t x1 plus 1 minus lambda okay, plus lambda w of t x1 prime plus 1 minus lambda v of t x2, right, plus 1 minus lambda w of t x2 prime. Okay, this is equal to lambda u of t plus v of t x1 plus w of t x1 prime plus 1 minus lambda. So I've broken up this u of t into lambda u of t and 1 minus lambda u of t, right? U of t plus v of t x2 plus w of t x2 prime. Right, and then these things are individually lambda x1 double prime plus 1 minus lambda x2 double prime, which is of course nothing more than y double prime. Okay, so this verifies that, so I should say that this is u of t plus v of t y of t plus w of t y prime of t. Okay, so that equality holds, right? You can check that. You can also check that Okay. All right. Actually, I guess the way the problem is set up is I don't want solutions of the boundary layer problem. I'm sorry. Okay, so I just want solutions of the ODE. Okay, so I just want to satisfy this. I don't really need to satisfy the boundary conditions as well, because I guess if we satisfy the boundary conditions, we'd be done, right? So apologize for that. Right, so yeah, so you can check that again, this convex combination of two solutions of the ODE again satisfies the ODE, right? And because of the fact that again the ODE is inhomogeneous in general, right, then you need a convex combination. Okay, it's not sufficient for it to be an arbitrary combination. Okay, all right. So I want to choose, so I need to choose lambda such that y of a is equal to alpha and y of b is equal to beta. Okay, so we know that lambda, so I'm just going to write down these conditions in terms of y of t being this convex combination of x1 and x2, right? So alpha is equal to y of a is equal to lambda x1 a plus 1 minus lambda x2 a, right? And beta is equal to y of b is equal to lambda x1b plus 1 minus lambda x2b, right? Those are the equations I need to solve. And you can check that that allows me to solve for lambda. Okay, so lambda is equal to beta minus x2b over x1b minus x2b. Okay. Okay, and then once you have that, it's like you have what you need. So obviously you need that x1b and x2b are not equal to each other. So we need x1b is not equal to x2b. Okay. Okay, so let's see how you can do this. Okay. So when we discussed the shooting base method, it's like what we saw was that one way to do this is to, construct some sort of shooting solution. So let's try to see whether we can do something like that, right? Okay. So I have x1 prime, x1 double prime is equal to u of t plus v of t x1 plus w of t x1 prime. All right, so that's the differential equation. And then let's say x1 of a is equal to alpha and x1 prime of a equals to z1. Okay. Then I'm going to write another equation which is similar but not exactly the same, basically with a different initial velocity. Okay. So x2 double prime is equal to u of t plus v of t x2 plus w of t x2 prime. And x2 of a is alpha as before, and x2 prime of a is equal to what I call z2. Okay, and then z1 is going to be different from z2, is the point. Okay. So I can find these simultaneously, right? I can have x0 prime is equal to 1. Okay, so I'm going to make it non-autonomous, right? Then x1 prime is equal to x3, x2 prime is equal to x4, then x3 prime is equal to f x0, x1, x3, and x4 prime is equal to f x0, x2, and x4. Okay, and then x0 of a is a, right? Because x0 is the time variable. It's a copy of time, we recall. x1 of a is alpha, x2 of a is alpha, x3 of a is 0. So I'm going to set one of the initial velocities to 0. I'm going to set the other initial velocity to 1. Okay. Right, and then I can find x1 and x2 simultaneously. Okay. All right. So let's see what the general theory it's like behind all of this is. Okay. All right. So we have we're going to break it up into 3 pieces, right? y0 double prime is equal to u plus v y0 plus w y0 prime. Y0 at a is alpha, and y0 prime at a equals to 0. That's one differential equation. Another one is y1 double prime is equal to v y1 plus w y1 prime. Then y1a is equal to 1, y1 prime of a equals to 0. Right, so this is inhomogeneous, and then these two are going to be homogeneous equations. Right, y2 double prime is equal to v y2 plus w y2 prime. Then y2 of a equals to 0, and y2 prime of a is equal to 1. Then you can check that the solution has the form x of t is equal to y0 of t plus c1 y1 of t plus c2 y2 of t. Okay, so this is the general form of the solution, right? Okay, and then yep. So let's see how they're related to this. Okay. So the solution for star is going to be x1 is equal to y0 of t plus z1 y2 of t. And then the solution for double star is going to be x2 of t is y0 of t plus z2 y2 of t. Right? So it's fairly easy to sort of see that these are sort of the ones which are relevant. So, all right. So if this linear boundary value problem has a solution, right, and what has to happen is that it satisfies the boundary conditions, right, which were the alpha and beta conditions. So alpha is going to be y0 of a plus c1 y1 of a plus c2 y2 of a, and beta is going to be y0 of b plus c1 y1 of b plus c2 y2 of b. Okay. Let's put 3 stars here. Okay. Right. So you can see right away that C1 has to equal to 0. So we can see okay. So x of t is equal to y0 plus c2 y2 of t, right, which is equal to y0 of t plus z y2 of t, where z comes from this sort of initial guess at the velocity, right? So this x prime of a is equal to z, right? So you can find c2 or z from sort of this equation, right? From the condition that beta is equal to x at b, which is equal to y0 at b plus c2 y2 at b. Okay. All right. So so from that I can figure out what c2 is. So there are two possibilities, right? So I have beta minus y0 at b, right, is equal to c2 y2 at b. Okay, so to solve for c2, it's like there are two possibilities, but in particular it has to do with whether y2 at b is equal to 0. Okay, so let's look at what happens there. Okay, so there are two cases. So case 1, right, so if y2 at b is not 0, then clearly c2 is just going to be beta minus y0b divided by y2b. So this is equivalent to x1b minus x2 of b, which is z minus c2, y2 of b being not 0, right? So this algorithm works like the one before. So this solution is like the one before. Okay. All right. So that's a second possibility. So if y2 at b is equal to 0, okay, which is equivalent to x1 of b minus x2 of b being equal to 0, then what it means is that x1 of t, which is y0 of t plus z1 y2 of t, is a solution of the boundary value problem. Okay. So that's basically the other possibility, right? Is that if this is actually 0, then you already had a solution to begin with, if you will, of the boundary value problem. Okay. So anyway, so the theorem is as follows. Right. If the linear boundary value problem has a solution, then either x1 itself is a solution, okay, or x1b minus x2b is non-zero. Okay. So basically, again, it's like you're either in a situation where one of the things you computed was already a solution, or if that's not the case, then you can construct a solution from the combination of x1 and x2. Okay, so right, so that's sort of the theoretical framework. And then what's going to happen next is that we're going to talk about how, in practice, it's like instead of trying to solve the ODE analytically, the initial value problem analytically, we're going to use it's like a one-step method to compute an approximation of the solution of the initial value problem, and then we're going to combine this it's like with the ideas we've sort of formulated so far to then construct an approximation of the two-point boundary value problem solution. Okay, so let me just stop here.